So the instruments that we decided to present to you are basic instruments that are now well known and that a lot of people are using worldwide. And it's to characterize the state of the snowpack. And we choose the most basic instrument from the classic ones, so the traditional ones, to some more modern ones. What is the latest tools that scientists are using?
And I mean, the properties we measure, obviously the fundamental properties of snow, which is the density, specific surface area, the grain size, and other properties. And yeah, as Nesh said, these properties we can measure them with a range of instruments. They are traditional measurement techniques, but they're also more advanced techniques that have popped up in the last years.
So with this range of tools, you will be able to go from different resolutions. So if you really want to have, let's say, a rough idea, maybe that would be more easy to perform, or really a detailed picture of the snowpack structure. So this you will have to choose depending on what are you interested in. So we focus here on the basic property of the snowpack, which are density. So obviously how much air and how much ice is in your snowpack. A lot of physical and mechanical property will be based on or depend on this density. And then characterizing the structure of the snow with the grain size, grain shape, but also the specific surface area. And we're also gonna go through different hardness, so with the hand hardness, with the ramsonde, or even the more detailed instrument is the snow micropen. Those are the basic properties to really characterize the structure of your snowpack.
There are many mechanical but also optical properties. If you think about albedo on the side of the optical properties, or maybe of the elastic modulus on the side of the mechanical properties, that relate to those fundamental physical quantities such as the density or specific surface area. So measuring these properties is very important to maybe also infer more advanced or more detailed mechanical or optical properties of snow.
We perform measurement. We are interested in knowing how does the snowpack looks like, because obviously this is needed for a lot of application related to the snowpack. Stability, so avalanche forecasting, how the snowpack reflects the sunlight, or in general the reflectance. So this is important for climate studies, how much the snowpack hold as liquid water, so because this is important for hydrology. Obviously we are not measuring everywhere on the planet. This is not possible. So measurements that we are doing here have been really used to develop snowpack model. So with this snowpack model you are able, given a certain forcing of the weather and of the atmospheric data, you are able to simulate the snowpack at anywhere and retrieve some properties depending on your application. And to guide the development and to evaluate how good are our simulation, how good are the snowpack models, we need those measurements to compare.
Another example could be satellite measurements. I mean, the satellites that are moving around the globe, we get loads of information. And also on the surface of our planet, there are large areas with snow. So to interpret the signal we receive on a satellite and to interpret these data, it's important to know what the snow does with the electromagnetic waves. And the measurements from the locations where the pictures were taken from the satellite, help to interpret also these data. Typically a good sequence of measurements is you choose a spot where you want to dig your pit, you think about the layout, how you want to organize yourself, what is the orientation of your pit gonna be, of the pit walls in particular. Then you perform one measurement of the ramsonde, and the ramsonde gives you actually already the hardness. And then you leave the ramsonde in place, you open the pit, and you can use the scale of the ramsonde to define your layers, do the traditional snow profile, and then comes the next measurements you want to perform, which could be the density. All right, so this is the Rahmsonde. It's an ancient tool. It's a penetrometer that is used to measure the resistance of snow layers in the snowpack, and consists of the rod that has a cone in the front and another rod that has a scale on it with a weight that can slide here. And the way it works is the probe runs into the snowpack, or is driven into the snowpack by the force that we apply when we lift the weight here. And we lift the weight at different elevations, and the force that is exerted here at the top drives the rod into the snowpack. The first thing we do is we measure actually penetration resistance. And to do that, we put the Rahmsonde on the snow surface, and we carefully let it penetrate into the snowpack. And you can see it penetrated a bit, and now it sits here, and I read 7 centimeters. So the penetration, skier penetration, is 7 centimeters. So this is the first number we write down. Then we apply the weight, and I can already anticipate what's going to happen. It's going to go deeper, because now the weight is 1 kilogram. So now we're going deeper. And now we're at 34. So this is the Rahmsonde and the weight.
34.
34. So now I'm going to lift the weight, and I'm going to start with very small increments because the snowpack's soft. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there was 8 times 1, and the depth was 36.
36.
And then there was 1,
1.
1, and now we got 46.
46.
So you see it moved down quite a bit, so I want to continue with small increments, small steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I released it 10 times, 1 centimeter, and now we got 48.
48.
Six times 20, 94.
91.
94.
94.
6 times 20, 94.
Mm-hmm.
So I think this is the snow depth now. We had 97. Yeah, it's got to be the ground. So the good thing about it is we measured hardness, but now we also know what the snow depth is. So we can keep the Rahmsonde right in the corner where we want to do our snow pit. So the Rahmsonde is now there, and we already measured the hardness, and we keep the Rahmsonde right there in the snow, and we want to arrange our snow pit around the Rahmsonde, because now it actually shows the snow depth, and it also has all the increments that we need to record the layering. So now we have several options. Either we cut this part here open, so we remove the snow here, and the Rahmsonde would sit in the right corner. And this is actually a good idea, because then the sun can't get into our snow pit and warm the snow surfaces. If we would go on the other side here and would open that side, which would also be possible, so remove the snow here, it's not ideal because the sun is on the right and it would hit the side wall, the left side wall of the snow pit. So what we're going to do is we're going to open right here. So we cut the sidewalls here with a snow saw. This way we get a really nice and clean cut. And now we can remove the snow from between the cuts. And you see the ramson here appears in the corner, and the scale on the ramson can be used for recording the layer afterwards. So here, when you cut the front wall of the snow pit and also the side walls, you want to keep your shovel in the right angle, that it cuts down nice and neatly, and that you end up with a nice clean snow surface. If you do that, you already see during digging, you can visibly already determine layers. I mean, there's some white above some gray, so there's gonna be a difference also in the properties of the snow. All right, this is about what you want. This is about what it should look like. The angle here is about 90 degrees, and you see we arranged it in a way that the probe is in the corner, and we have two walls to work with, and none of the walls in our case is actually in the direct sunlight. So when we work here, we can look at the grains, we have a shady area, and also the surface is not melting before our eyes. We start with the first measurement in the snow pit, and this is the temperature measurement. We start with the surface temperature. If you want to measure the surface temperature of the snowpack, you got to put the temperature sensor, which is here at the tip of this needle, you want to put it right on the surface, that it touches the snow, but it doesn't go into it doesn't stick in the snowpack. You want to have the needle at the surface. And you want to measure the temperature in the shade. That's why I placed my shovel here, to produce enough shade for the temperature measurement. So that's the first temperature we're going to write down, and our thermometer reads here 0 degrees Celsius. So we got 94 centimeters of snow. So the snowpack has a depth of 94 centimeters. We just measured the snow surface temperature. The next measurement we take is at 90. And this is the first temperature in the snowpack, and it reads 0.1. And we go down to 85, and it reads 0.3. The next number you should write down is 0.5. Okay, so let's have a look at the tools we use for traditional snow profiling. Here you can obviously see a magnifier, and it's a convenient one that sits on the crystal card, so it's always in focus. This is the crystal card, and you can see on this crystal card or crystal screen there are different grids. There's a millimeter, a 2 millimeter, and also a 3 millimeter grid. Crystal cards are very thin, that they slide nicely into the snow cover, and they're black. This way we see the white crystals very well. Here there is a ruler. The ruler helps to measure, but can also help to identify layers, as we will see later. There's a pencil. We need this pencil for hardness, and there's also a little knife for hardness observations. And the hands. So now we want to go ahead and find layers in the snow pit. And there are several ways to find layers, and basically all these methods, they are based on our senses. So first thing we can do is we can just look at the snow pit, and here you can already see differences in color. I mean, here it's white, there it's kind of gray, and there's something more dark kind of gray down here. The next thing you can do is, while you move the crystal screen on the snow, you will also hear differences. So you see the layers down here, they sound very different than the layers up here. And finally there is a third way, and that's the tactile way. You could run a ruler through the snowpack. And there would be a place where it's getting harder, like here, where it's getting harder to run the ruler through. Another way, also visual, could be to put a crystal screen behind scrape off some snow, and then you can see very nicely the differences between the layers, because the dark crystal screen from behind changes the appearance of those snow layers. Then we can also use our hands. Up here it's very soft, here it gets harder. You can see up here my finger went in deeper than here. Let's continue. Oh, here we're going deeper. Here it's very hard. Here we go deeper again. So here, with my fingers, I could already identify the top, which is very soft, a harder part here. Then from about here it gets softer again, harder, thin soft layer, and hard again. And all these pieces of information, I want to put them together and maybe mark those layers. I could draw little lines here that help me later not miss them when I go through them. I tagged the layer interfaces that I identified before with my finger, and also with the help of the crystal screens and by visual identification. So now for every layer here, I would like to write down 4 properties. The first property is the wetness of the snow. The second one is the grain type. The third one is the grain size, and the fourth one is the hardness. The snow temperature in the first layer is below 0 degrees, so it's not wet, it's dry, per definition. Let's have a look at the grain type of the first layer. So I take my crystal screen and I take a small sample of the first layer, and I have a look through the magnifying glass, and the question is that I ask myself, how many grains can I fit into one box? And here on the 1 millimeter grid I can actually fit only half a grain into one box, so the grains have a size of about 2 millimeters. The grain type is graupel. It's a precipitation particle. And the fourth piece of information I need is the hardness.
So for the hand harness, you will first use your hand, and we do fist, forefinger, 1 finger, then it's pencil, and then it's a knife. It's the knife doesn't go in, that means you are in a layer of pure ice. So you are in your layer and you will probe and try what's go in and how hard it is to go in. So first the fist, it's not getting quite go. Forefinger, 1 finger. So here it's going with 1 finger, I would say. If it's not, you continue with the pencil and finally with the knife. If not, a knife cannot go through, that means you are in a layer of pure ice. The force you want to put when you are probing your layer is basically the force you will press if you want just to press on your nose. So you go in the layer and then you start pressing. For the grain shape, there are 6 main types of snow. Fresh snow, fragmented particles, rounded grains, faceted crystals, depth ore, and melt forms. And they have some characteristics that helps to identify each of them. So precipitation particles or fresh snow is the typical snowflakes you will see falling from the sky. Fragmented particles, you will still see some branches. Rounded grains, they are small and round. Faceted crystals are a bit bigger and you will see some angles and some facets. Depth ore, they are often even bigger and you will see some striation on the ice surface. They can have these pyramidal shapes and also some sharp angles. Then we have melt forms, and as the name said, the melt form have seen some liquid water. So they are rounded, they are clustered together, and they are big. So what you see here is like big clusters of grain that are kind of glued together because there have been some liquid water in it, and those are called melt forms, and they are quite big. Those are between 2 to 3 millimeters. For each layers you have to give one grain shape. Those are the main 6 types, and you can have, because it's nature, you can also have transition, and that's get a bit tricky, but you have transition between shapes. So now we're going to record the density profile. So density is really the basic, most important property of snowpack. It will give you the proportion of air and ice which are in a layer. So if there is more air, it's not as dense. If there's more ice, it's more dense. For that, the method is quite simple. We are basically collecting snow, a given snow volume. So you can have different holders for that. The ones that I show you now are cylindrical, different size depending on the resolution you want to have and the size of the layer. You can also have some that are rectangular or triangle, different shape exists. But basically you are collecting a given snow volume and you are then weighting it. So you have the volume, you have the mass, and the density is then just the mass over the volume. So for that you need density cutters, as we call it, and a scale. You can either do density profile at regular heights along your pit, or you can also do density per layer. So you use the layer that you identify in your traditional profile, and you will give in addition to the other parameters one density value per layer. Here we are interested in having a continuous profile, so we will do a density profile every 3 centimeters at regular height. Ben is now doing the first measurement on top of the snowpack, so he's inserting this density cutter till he reaches the crystal cords. This way we'll get the exact volume of snow he needs. Alright, so
75 is the density.
233 to 236.
So this part we already measured, so we take it off.
Yeah.
Clean surface, and now we want to see how deep the cylinder would go in. It would go until here. So we push in the crystal screen as a boundary, and then we can insert the cylinder. Cylinder is in, and now we want to remove the snow from around the cylinder.
Alright, so that's now 200. So 2, 3, 6.
199, 200. Right in between.
199. So this is now way denser than the first layer.
Okay, so what's the next layer we're doing?
Second layer,
This way we continue all the way through the snowpack until we get to the bottom and we obtain a regular spaced profile of snow densities with an interval of about 5 to 6 centimeters, depending on the size of your cutter. Our cutter here has a diameter of 4 centimeters, 1 centimeter at the top, 1 centimeter at the bottom, gives 5 centimeter intervals for this type of cutter.
When you perform density measurement, there's only two things that can go wrong. It's either in your given volume you are putting too much, you are compressing your snow, so you are having overestimation of the density, or you are in the other way around, putting not enough snow into your snow volume. So those are the two things you have to be careful at. Get just right the volume you need.
All right, so this old guy here is called doofus. That stands for Dual Frequency Integrating Sphere for Snow Specific Surface Area Measurements. And it's the, I will say, the ancestor of all optical instruments to measure in the field the SSA. So the SSA, or Specific Surface Area, is a way to measure, to put it simply, the grain size, or more into detail, it's a way to measure the interface between ice and air within the snow matrix. And so it is measured in square meters per kilograms. And with this instrument here, we can measure it directly for several samples. And here we have some tools to prepare the samples. This is the sample holders. This is another sample order. This is just to prepare the samples, and here we have what we call the spectralums, so to calibrate the instrument. So here we have 6 spectralums, different colors, of course. So the reflectance is different. Here is 5%, meaning that only 5% of the light hitting this sample will be scattered back to our receptor, and here is 99% more or less, the white one. So it is that the reflectance is very well known, and we measure directly with our instrument every day, every time we perform a measurement, the voltage. And so we have a curve, a calibration curve with voltage and reflectance with 6 points. So doofus works like this. Inside this cube here, there is an integrating sphere. So it's basically a sphere, white sphere. We have a diode here at 1310 nanometers, which is in the infrared, and the snow sample will be put here. So basically we have the light coming from here. It will be scattered back by the snow sample, and the sphere will collect all the light, and that light will go to the receptor here, and finally it will be displayed by the LED here. So basically we measure like this a voltage, and then using our 6 spectrums here, we can convert our voltage measurements into reflectance. So basically it's a 3-step measurement. What we get at the start is a voltage, so millivolts here. Then using a calibration, we convert our voltage into reflectance, and then back to the lab from reflectance to SSA. Alright, so what we want to do now is we will take several measurements at different depths into the snow. Because of course with doofus you can just stick to the surface and measure the SSA of the surface layer, but you can also perform a vertical profile for different layers. So as I said before, we have one measurement representing 1 centimeter of snow. So we can go 1 centimeter down each time. So we can start measuring, for example, here. So here we are at 2 meters. Here we go. Sample is ready. Put it down here. So Neige on her logbook will have two columns. On the left hand side the depth, and on the right hand side the voltage, which is now 510. 510? Yes, millivolts. That's it.
Alright.
So when the snow height is, for example, 200 centimeters, it means that the measurement has been taken between 200 and 199, right? And when our measurement is between is at 198, so it means that we have measured the snow between 198 and 197. Depending of the snow type, if it's very hard, it could be tricky, but otherwise you just insert the holder like this, and then you try to free it from the snow a little bit like this. Then, first tricky part is now here. You really want to clean it up, so you want to do like this, more or less, right? And then you turn it upside down. Snow is a little bit sticky today because it's a little bit wet, but this is already a nice sample. The idea is that you really want to have something at the same level of the holder, so you want to clean it up a little bit more. So you can here very gently press it a little bit like this. All right. Basically, you don't want to destroy the bonds between grains, otherwise you will change a little bit things. Or you can this way remove the very top layer. You just scrub it a little bit like this, and here you are, right? Here we go. So this is a nice sample, and the spot of the laser is about that size, so it doesn't matter if the edges are not perfect. The laser will look at the snow more or less like this, like here. So this is the most important part, I would say, of your sample. Here, if you want to put it simply, we measure really just the reflectance. So how much light is scattered back at this particular wavelength by the snow. And just when we get back to the lab, we have an algorithm which has been calibrated on the method absorption method, and using that algorithm we are able to retrieve directly the SSA. But this is just a step further. For now, this as an instrument just to measure the reflectance of snow.
Okay, so the device that I'm going to introduce to you now is the so-called Snow Micro Pen. The Snow Micro Pen is one of those instruments that are called penetrometers. So you see it has a long rod, and you can already imagine what it's going to do. The rod will be driven by this engine into the snowpack. Those penetrometers were developed at the end of the 90s, and from then on they have been further and further developed, and the version I hold here in my hands is from 2015. I said it measures penetration resistance, and penetration resistance is a force that is recorded when the rod is driven into the snowpack. So at its tip sits a little sensor, and I'm going to show you here the tip. Here comes the cone, and there is a tip, and right behind this tip here sits a sensor that records force, so Newton. And we are interested in the penetration resistance, which gives us an idea of the hardness of the snow that the Snow Micro Pen runs through. But more importantly, algorithms allow us to recover 3 microstructural parameters from the penetration force, which are the rupture force, the deflection at rupture, and a structural element length. And now you actually see what is really the nice thing about it is we don't only learn about the strength or the hardness of the snow, we also learn about how much it bends. So we learn something about the elasticity, and we can also learn something from the signal about the structural size of the grains. Based on these 3 microstructural parameters, we can derive a number of important snowpack properties, such as the SSA, the specific surface area or the density or even the elastic modulus of snow layers. So when you switch on this controller, the controller, actually the menu guides you right through the process of driving the rod back and forth or performing a measurement. And what we're going to do now is we're going to perform one measurement. The important thing with the snow micropen is that you want to do the measurement slope normal. You don't want to measure perpendicular. And this is important because the sensor that I just showed you is very fragile for shear movements. So if you have a layer, you want to work perpendicular to this layer and you don't want to have a shear component. That's why we measure normal, slope normal. The 2 feet help to position the instrument. And then in the menu we go to measure and press the start button. Now we have to hold the device very carefully, don't move it. Okay, so this is how fast one measurement is, and it's important to have enough pressure on the instrument that if there is a harder crust, that the engine is not pushed upwards, and when the rod is driven into the snowpack, it's driven by this engine, and when it comes back up, the engine is reversed and it comes up with a higher speed. And a little brush here that sits in the front actually cleans the rod, that there is no snow going into the engine. Depending on how hard snow layers are, you can imagine the crust of a thickness of several centimeters, the device might shut off. It depends on how hard the crust is and if there is a so-called overload. And there is a certain danger that the sensor might break with this overload. The device shuts off. Now after the measurement, I can look here on the display and I can get a rough idea of what the layering is like. And these data, they are saved on a memory card, and I will look at them when I'm back at the office. So this is just a rough idea to see, there are crusts and there are certain layers that I've maybe identified in the profile that I know about what we're measuring. The special thing about the snow micropen, what makes it different from other penetrometers, like the ancient Ramsonde for instance, is its resolution, its sensitivity and the constant speed. Resolution. You need a certain resolution to actually resolve all this braking that happens at the tip when the cone is driven into the snowpack. And this braking that happens is well below 1 Newton. So this sensor here has a resolution of about 1/100 Newton. So 0.01, 0.02 Newton. And resolves actually the braking of grains around the tip. When we measure, we also want to have a very high number of measurements within a short distance. And this sensor here records the signals, 250 signals per millimeter. And this allows us actually to resolve microstructure, because we know that grains are well below 1 millimeter. And if these grains break, we need a very high resolution of the distance, and we need to know the exact position of the sensor while it runs into the snow cover. And the third element is the constant speed. And snow deforms differently depending on the deformation speed. Only then we can derive reliable parameters. If the speed would change, also the behavior of snow would change. Here is a little piece of advice for your first measurements with a snow micropen. Keep it cool. That's very important. I usually make a little hole in the snowpack here, and then I go in the menu where it says drive engine, and I drive the rod into this hole here in the snow cover, and this keeps the rod and the sensor cold, and then the snow micropen is ready for measurements that you want to take later. If you don't do that, there might be snow sticking on the rod, and the rod is always outside, so it might absorb solar radiation and get warm, and then water runs into the gearbox and can actually cause problems of the little chain wheels. So keep the tip cold and make sure there's no snow here on the rod. I think those are key elements to get good readings from the snow micropen.
So this instrument here is called WISE. So how does it work? Basically, it has to be put into the snow, and it will measure the liquid water content of this sample within. So it's the percentage of liquid water within snow. And it basically can be computed in terms of mass or in terms of volume, and this instrument will give us both. The principle is based on the fact that density, liquid water content, and the dielectric constant or coefficient of materials are connected by an equation. So if you know density, and if you are able to measure the dielectric properties of the snow, you can retrieve your liquid water content. Or, for example, if you already know that your snow is dry, so the liquid water content is equal to 0, you can use this guy to measure directly the density. It needs to be turned on, so this is the bottom. And it will require a calibration, first of all. So we have to press this button here, air, and leave it like this in the air, and it will be calibrated this way. And then validate the measurement, and it is saying here put sampler into snow. So that's what we will do. We will measure, for example, snow right here. All right. Once the sampler is inserted into the snow, we can press this button once again. It is saying measuring. It will say the permittivity is 1.313, all right, and then it will ask for a density. As I said before, it needs density as input. So the density of this layer was about 170, so I can try to write it down. 170 kilogram per cubic meters. I press OK once again, and here it is. So here we are reading liquid water content in terms of volume is 0.41, and liquid water content in terms of mass is 2.39. All right, so it's not perfectly dry. There is some liquid water inside. Once the measurement is done, you can press this button once again, and you're able to measure another layer. So you use this tool here to remove all the snow. Almost. If we want, we can perform an entire vertical profile, perform measurement into the snowpack all the way down. And for example, we choose another layer here. Here we go. Press OK. The density
255.
255. to 55. And here it's completely dry, so it's 0 everywhere. Liquid water content volume 0, liquid water content mass 0, right? So we are into a dry layer.
If there's like a last message, get the tools, watch the videos, get involved, play in the snow, and while you play there, it's try and error, and you will pick up some routine and learn something about the snow cover.